given that we have these two vector representations, one thing that you want to be able to do is you want to be able to go between one form and another. So what we're going to do here is we're going to take a look at how you might go from a vector represented in Cartesian notation, or with an x and a y coordinate, and put that into an angular notation. So what you'll see here up at the top is I have a vector that is in Cartesian notation, and it has an x and a y coordinate. Underneath it, you'll see there's a Cartesian plane. What I recommend you do first, before you do anything else, is first of all, draw yourself a rough arrow for where it should be in the Cartesian plane. So you'll notice here that the x coordinate is negative, which means we're going to be going to the left, and the y coordinate is positive, so we're going to be going up. What that means is my vector arrow, right, again, this is not drawn to scale, should be going left and going up. Now, what you're going to do the minute you draw this is you're going to turn this into a right angle triangle. Because if you take a look at the standard toolkit of trigonometric tools, they are all well related to right angle triangles. So what we're going to do here is it does not matter where you do this, but you're going to close off this vector and convert it to a right angle triangle. Now, the nice thing about this is if you're going to use the right angle triangle formulation of trigonometry, the signs, you got to deal with them yourself. So we're just going to say that we're going 5 units left and 4 units up. And this is our standard picture. Now, our goal when we convert this to angular form is we want the magnitude of the vector. So we want r here. And we also want an angle. Now, the easiest angle to use is always the one next to the origin inside your triangle. Now, with that being said, if we find r and we have find theta, we're finished. So our first goal is to find r. If you take a look at your trigonometric toolkits here, there are 4 different trigonometric tools you can use. You can use the Pythagorean theorem, which is the one up the top, and you can use sine, cosine, and tangent. It doesn't matter which one you pick. Like, they're all interchangeable. However, one thing I will tell you is if you are finding the magnitude, the one that you want every single time is the Pythagorean theorem. The Pythagorean theorem's sole job is to find the magnitude of vectors. So here we have r squared is equal to x squared plus y squared. If we were working in 3 dimensions, we would just have r squared is equal to x squared plus y squared plus z squared. So with this, we can actually use this to find r. Again, we're going to put the signs in ourselves, so we don't need to worry about positives and negatives. So the simplest way to deal with this is just to treat everything as if it were positive. Be very careful if you are using, say, -5 here. Because if you type this as -5 squared, it will come out wrong, because this is not the same as -5 squared. If you type this in on your calculator. They don't come out the same, because your calculator assumes that you are doing order of operations properly. All right, so the safest way to do this, if you're going to use the right angle triangle formalism, ignore all the signs. Put them all in yourself at the end of the day. Now, with that being said, we can actually solve this fairly quickly. There's no tricks here. It's just a single variable algebraic equation for you to solve. If you've done it properly, you should get r is equal to around 6.4. And that is one of the components that you need in order to convert this. Now, the second thing that you need is you need to find the angle. Now, you could use sine, cosine, or tangents. They all have the angle theta in them that you want. However, what I will tell you very specifically is the best one here to use, even though you could technically pick whichever one you want, is tangent. And there's a reason why you might want to pick tangent. If you notice, tangent here deals with the opposite and adjacent sides. In other words, the tangent function deals with quantities that you were given in the question. Sine and cosine require you to know this hypotenuse, or this magnitude r. Tangent does not. So if you messed up finding the hypotenuse, it won't matter if you use tangent. Now, to use tangent, you need to be able to identify the sides that you have. Now, we have tangent of theta here. We don't know what theta is, so we can't simplify this. However, on the other side, we need to use the opposite side divided by the adjacent side. The opposite side is the side that does not touch the angle, which is the 4. The adjacent side is the side that does touch the angle that is not the hypotenuse, which is 5. You'll notice here, again, we're not putting in any signs. If you are using right angle triangles, do not put the signs in when you're doing your math. Simply add them at the end. Now, with this being said, you do need to be able to solve this. Tangent is a function here. To remove it, you're going to use an inverse tangent function, and you're going to apply that inverse tangent function to both sides. I always write the inverse tangent function as a tangent because in comparison to most of you, I'm pretty old. If you're using a computer, please use atan. It's the one that works. On your calculator, though, this is probably written as tan to the negative 1. Now, when you are using these inverse tangent functions, the settings on your calculator do matter. So if your calculator is set to degree mode, your angle will come out in degrees. If your calculator is set to radian mode, your angle will come out in radians. My calculator currently is set to radian mode. So I am going to get an answer that is in radians. And the answer that I'm going to get that's in radians seems small, but it's actually a sizable number of degrees. So if you do this in radians, you get about 0.67 radians. Now, if you were doing this in degrees, and again, it's going to depend based on what you want, but if you do this in degrees, this 0.67 radians, which has no units because radians are dimensionless quantities, is equal to about 36.7 degrees. And you'll notice here, whenever you write things in degrees, you either need the degree symbol or you need the word there, because degrees are effectively a unit of measure. Now, with that being said, we can put this all together if we were to write our vector quantity. So vector A here is going to be equal to the magnitude of A, which is roughly 6.4. And as for the direction, we need to do a couple of things. First of all, we need our reference direction, or the direction that our angle touches or starts from. This direction, of course, is to the left. That's where we're starting. We then have our angle, I'm going to use radians here, of 0.67. And then finally, the 0.67 is left and then tries to point upwards. So it starts going left, and then it rotates and touches our hypotenuse, moving towards the upward direction. And that would be converting our vector from Cartesian form into angular form.